Have you ever really stopped to think about how a simple piece of glass, a lens, can show you a galaxy light years away? Or how it can correct your vision so you can see perfectly? It feels a little bit like magic. Well, today we're going to pull back the curtain and show you the simple, really elegant secret behind all of it.
When you think about light, you might picture something like this: expanding waves, kind of like ripples on a pond. It feels incredibly complex, and honestly, in a lot of ways, it is. So the big question is, how do we get from this beautiful chaos to the super precise, predictable world of eyeglasses and telescopes?
Well, the answer is kind of beautiful in its simplicity. We just create a useful shortcut. We trade the messy reality of waves for a much cleaner, much easier model. We decide to treat light not as a wave, but as a bunch of perfectly straight lines, or rays. This is the whole idea behind geometric optics, and it is the key that unlocks everything else we're about to talk about.
So, here's our game plan. We'll kick things off with the basics of what geometric optics really is. Then, we're going to uncover this key property of light called vergence. From there, we'll see how lenses mess with this property, learn the simple math behind getting a perfect image, and finally, see how it all scales up to build amazing things like telescopes.
All right, first up, let's get properly introduced to our new best friend, geometric optics.
At its heart, geometric optics is just a super powerful simplification. It gives us a set of rules that lets us basically ignore all the complicated wave stuff and just focus on the path these light rays take. And by thinking in straight lines, we can precisely figure out and predict how light is going to behave when it goes through, say, a magnifying glass or a camera lens.
Okay, so we've got these light rays, but what good are they? What information do they carry that's actually useful to us? Well, it turns out they have a kind of secret power. And to get it, we need to dig into their most important property, this concept called vergence.
So to understand this, let's start with a single tiny point of light. Just like if you dropped a pebble in a pond, it sends out these spherical wavefronts that just expand out in all directions. And you can see, right up close to the source, those waves are really curved.
Now just watch what happens as these waves travel farther and farther away. See that? The curvature gets shallower and shallower. They start to flatten out, becoming way less spherical as they expand.
Finally, if you get far enough away, what physicists call optical infinity, the curvature is practically zero. The wavefronts are basically parallel lines at this point. This is what we call a plane wave, and it's the perfect way to think about light coming from something super far away like a distant star.
So this changing curvature we've just been watching, it has a name: vergence. Vergence is literally just a number that measures how much a wavefront is curved. It's a single value that tells us everything we need to know about whether a bundle of light rays is spreading apart, coming together, or just traveling in parallel.
And of course, we need a way to measure it. That's where the diopter comes in. Now, it sounds technical, but the idea is actually super simple. For light that's spreading out from a source, its vergence is just -1 divided by its distance from that source, in meters. So if light is coming from a 0.2 meters away, its vergence is -1/2, or -0.5 diopters. That minus sign is going to be really important. It tells us the light is spreading out.
And this sign convention right here. This is the crucial takeaway. Light that's spreading out from a source, we call that diverging light, it always has a negative vergence. Light that's being focused down to a point, converging light, that has a positive vergence. And what about that light from a distant star? Well, its wavefronts are flat, right? So it has zero curvature and zero vergence.
Okay, now that we get what vergence is, we can finally talk about the tools we use to change it: lenses. Let's see how they actually work their magic.
So here we see the two main types of lenses in action. Over on the left, you've got a converging lens. It takes in those parallel rays, which, remember, have zero vergence, and it adds positive vergence, forcing them to meet up at a single point. Then on the right, the diverging lens does the exact opposite. It takes those same parallel rays and adds negative vergence, which makes them spread out.
But how? How does it do that? It all comes down to one simple fact. Light actually slows down when it travels through something like glass. So for a converging lens, which is thicker in the middle, the center of that wavefront gets slowed down more than the edges do. This causes the whole wave to kind of pivot inward. A diverging lens, on the other hand, is thinner in the middle, so the edges get slowed down more, making the wave bend outward. It's really all about the shape.
So,
We have light, and it has a starting vergence. And we have lenses which can change that vergence. You can probably see where this is going. Let's put it all together and see how we create a sharp, perfect image.
The whole process is really just a simple 3-act play. First, light leaves an object, and it has a starting vergence. That's just based on how far it is from our lens. Second, that light hits the lens, and the lens adds its power, its own chunk of positive or negative vergence. And finally, the light comes out the other side with a new final vergence. And that number tells us exactly where the sharp image is going to form.
Now here it is. This is the simple secret we've been building up to. The final image vergence is just the starting object vergence plus the power of the lens. That's it. All the complex physics of making an image, for our purposes, boils down to a single, simple addition problem. It's that easy.
Let's look at this in action right here. So light leaves an object on the left, at some distance we'll just call z. It travels to the lens with some amount of negative vergence. The lens then adds its power, and boom, the light comes to a perfect focus on the right, forming a sharp image at a new distance, z prime. It's all just simple addition.
So if the fundamental rule is really that simple, what can we actually build with it? Well, let's scale things up and see what kind of possibilities this unlocks.
You look at something like a telescope, and it seems impossibly complex, right? But at its core, it's just a series of lenses applying our simple addition rule over and over again. The first big lens gathers the light and does the first vergence calculation. Then a second lens takes that light and does another vergence calculation to give you that magnified view. It's just simple math, one step after another.
And you know what? You don't even have to look to the stars to find a sophisticated optical system. You're using one right now. Your eye's cornea provides a huge amount of fixed focusing power, and then that little flexible lens behind it fine-tunes everything. Together, they are constantly, every second, doing that exact same vergence calculation to create a sharp, perfect image on your retina.
So we started this whole journey with chaotic waves. We simplified them into predictable rays, and we found out that the big secret to bending light and forming an image is really just simple addition. The next time you put on a pair of glasses, or look through a camera, or just, look at the world, remember the elegant physics that's happening. The only question left is, what do you see differently now?